Section 5.4, as you can see, has a name that should kind of wake you up. The fundamental theorem of calculus. You can't ask for a better name for a theorem. And I didn't write this. I copied this PowerPoint from a guy named Greg Kelly. He's online. He's got a bunch of PowerPoints. And this is his PowerPoint, so I can't take credit for this, but I like what he says here. This is, I guess it would be hard to express to you how important this theorem is, although maybe just by the name of it you'll put thought and time and effort into it, because it certainly is a powerful theorem, one that has many practical applications, and you're really not going to get the full benefit of it, and at least appreciating it for a while. So you just have to trust me that this is a very, very important theorem, and we're going to talk about it and do some examples, and it will, well, it'll make more sense as we go along, but basically it's this. The derivative of the integral is equal to the function. So let's recap this. We have the derivative of the integral from a being a constant to x, some random function value of x, of the function f lowercase f of t dt, and this is equal to lowercase f of x. Okay, so keep that in the back of your mind right now, and we're going to talk about that. So the fundamental theorem of calculus, this is part one. We now are defining functions as integrals. Okay, so notice that capital F of x is the integral of lowercase f. Okay, now f has to be continuous over a closed interval, and the function f of x has a derivative at every point, and the derivative of f is the derivative of the integral. Since capital F of x represents the integral of lowercase f, then we would say that the derivative of uppercase f is the derivative of the integral, which is just f of x. Okay, something to also keep in mind. Well, let me show you the next slide. I'm hoping that you're writing these things down and taking good notes here. It's going to be important. Now, notice here that you're taking the derivative of an integral, okay? And notice that these are the important things here to recognize, that the derivative that you're taking, the variable that you're taking the derivative with respect to, sorry, let me say it again. The derivative, okay, one more time. The variable that you're taking the derivative with respect to, which is x, matches the upper limit of integration. Okay, the derivative matches the upper limit of integration, and that also matches that variable. Okay, so these variables are all the same thing. Okay, now that has to be just x as well. Just x. And if that's just x, then that's just x. Okay? I would like to also forewarn you that you're going to see something like this. I'll put this over off to the side here. The derivative with respect to x of some constant a to x squared of f of t dt is not equal to f of x squared. Okay? What's your first clue? The first clue is that guy is not just x. That's not just x. So if that's not just x, all bets are off. Understand? All bets are off. It's not equal to f of, it's not equal to just f of x squared. Okay? So the only time when you can say that the derivative of the integral is just the integrand, by the way, I don't think we've defined that. This guy right here, this is what we call the integrand. So the derivative of the integral is the integrand with an x in place of the t. Okay. I realize that I'm giving you a lot of build-up without really giving you any problems here, but we'll see some problems here in a bit. The lower limit of integration must be a constant as well. It's got to be a constant. And we have the derivative of an integral. Okay? So let's move right along, shall we? We have part 2, Fundamental Theorem of Calculus, part 2. And part 2, this is just amazing. By the way, I'm going to prove this when we get to class next time. Prove this. Kind of a cool proof. In fact, it's a great proof. If f of x is continuous on the closed interval, and if capital F is any antiderivative, now I should probably define that as well, and I will. Capital F is any antiderivative of f, meaning that the derivative of, I should write that down now, and then I will expand on that a little bit more. The derivative of f with respect to x is equal to f of x. Okay? And so every time you go forward, you're taking the derivative. So the derivative capital F, in other words, f prime, capital F prime of x, is lowercase f of x. That's what the Fundamental Theorem of Calculus says. Part 1 says that the derivative of capital F is lowercase f of x. Okay? Which, when you go backwards, let me say one more thing. I just don't. That's the hard part about doing the videos. I don't know if you're sitting there going, "Yeah, I got it," or if you're looking at me like, "I don't understand." But remember, if you go from f of x and you go to the right, meaning that you're taking the derivative of f of x, we write that as f prime of x. Then you go to the right again, the derivative of f prime, or the rate of change of f prime, is f double prime. Okay? But if you go backwards, the antiderivative of f prime, the antiderivative would be lowercase f of x. Okay? The antiderivative of f double prime is f prime. The antiderivative of f prime is f, lowercase f. And the antiderivative of lowercase f is capital F of x. Okay? So you thought your life was great and complete when you had 3 functions that you were dealing with in Chapter 4. Remember sections 4.1, 4.2, and 4.3, where we analyzed f of x by taking the first and second derivatives and increasing, decreasing, concave up and down. Well, now it is even more complete that you now have a 4th function that we are referring to as the antiderivative of lowercase f of x. Okay? So we have capital F of x, and I think that's all you probably need to hear about that. But the way, and I did get a couple of comments like, Mr. Hawks, how do we actually find the value of this definite integral? Remember, we did definite integrals in our most recent videos, but now instead of just having to graph the function and calculate the net area between the curve and the x-axis between a and b, now we have this amazing theorem with just tons of practical applications in which all we have to do is find any antiderivative of lowercase f of x and evaluate that antiderivative at the upper limit of integration minus that antiderivative evaluated at the lower limit of integration. Okay? I mean, this is so amazing. Amazing that people figured this out, for one. But again, like I said, I'll be proving this theorem for you guys in class, which is, like I said before, an amazing theorem. Dropped my pen. So let's recap what we just talked about, and that is this. Remembering the natural order of things, like I just basically discussed with you, we started here way back when with f of x. We got to chapter 3 and we introduced the derivative. Then we got to chapter 4 and we said, hey, check this out. The derivative tells us whether f is increasing or decreasing, but the rate of change of the derivative, f double prime, tells us whether f is concave up or down. The rate of change of, oh my gosh, I'm sitting, I don't know if I mentioned this, I'm sitting in this car right now outside my daughter's soccer practice, and there are, look to be about 1,000 crows in these trees right behind me. I don't know if you can hear them or not, but that's what that noise is if you happen to hear something different. So that got us all the way, let me go with my pen here that I dropped. That got us all the way from way back in algebra to chapter 3 in Calc BC, and then here we had chapter 4, and here we are now in chapter 5. Don't worry, there's no more to talk about. This is it. Okay? So we have our capital F of x, which is just the antiderivative, or an antiderivative of lowercase f, and as you continue to take derivatives, you move to the right. As you take antiderivatives, you move to the left. So that's 11 minutes of build-up without doing any problems, so good job sitting through that. And take out your next worksheet, and we're going to go ahead and work through some problems. But I'm going to stop the video now and pick it up in the next video, so that if you ever need to go back and kind of remember these kinds of things, you can do that. So there you go. I will see you in the next video.